All right, so welcome to Chem 395 in the experiment about NMR or nuclear magnetic resonance. So here we will learn about NMR peak assignment and how to calculate equilibrium constants for acetylacetone. So before we start, let's take a look at the compound that we want to study, acetylacetone or 2,4-pentadiol. So we know that this is acetylacetone with two carbonyl or in ketone forms. So we call this molecule to be in its keto form. The keto form of acetylacetone is in equilibrium with another form where one of the hydrogens here jump to the carbonyl and forms what we call an enol. So shown here is the two possible enol forms of acetylacetone. The reason why we have two different enol forms is because we have two carbonyl, so there is two possibilities for the proton to jump into. So it can either form the enol with the carbonyl on the left side or with the right hand side here. So in the two enol forms here, they actually exist in equilibrium as well. So we cannot actually distinguish between because of symmetry. So for the ease of thinking about the process, you can also think of the enol form as a resonance between the two enol in the left or the right hand side. So it doesn't matter. We understand that now the two groups are equivalent, right? They have this resonance, and the hydrogen can jump between the left and the right. No, but all in all, now this molecule is symmetric. It's similar to what we saw in the keto form. Okay. So now, before we also move forward, we also need to think about how we will label the positions of these carbons and their protons. Okay. So first, let's take a look at this carbonyl in the keto form. So when you have a carbonyl in your organic compound, the carbon immediately next to this carbonyl is called an alpha carbon. So this is an alpha carbon, and this is also an alpha carbon. The one next to the alpha carbon is called a beta carbon, and then next to that it's called a gamma carbon. So this is labeled relative to this carbon. Right. But now, because this molecule is symmetric, instead of thinking about this carbon as an alpha carbon, we can also recognize that coming from this carbonyl, this is going to be a beta and a gamma carbon. So now we know that when we talk about the alpha carbon, it's about the middle one, while the gamma carbon is the terminal here. And the same applies when we look at the enol form. So this is still your alpha carbon, and that's your gamma carbon, while the carbonyl groups are located at the beta position. Okay. All right. So now, with all of this information, now we can start thinking about assigning peaks on the NMR spectrum. Okay. So the first step that we need to do in doing in interpreting NMR spectra, first we have to recognize the different groups of protons that exist in the molecule. Now this is more complicated for acetylacetone and its various derivatives because of the fact that in the NMR spectrum you will see peaks coming from the keto form and the enol form all together because they exist in equilibrium. So before we get into the gory details, let us first identify the group of protons for the keto form, and then we'll go to the enol form. Right, so in the keto form, we recognize that these two metals, they are equivalent, right? So they are just one group of proton. So we will call them the gamma metal. And there is another group of protons sitting here in the alpha carbon, which is in the form of CH2. Now, if we look into the enol form, again, we recognize that there are the terminal or the gamma metals. There is the alpha carbon that has now only one proton. And now there's also an OH proton, right, which comes from the CH2. So the CH2, one of the hydrogen or the proton stays here, the other one becomes the OH. Okay, so we've identified the different groups of protons in these two compounds. So if we count, we have 1, 2, 3, 4, and 5. So 5 different groups of proton, which translates into 5 different peaks in the NMR spectrum. Okay, so now we know we will see 5 peaks in the NMR spectrum, but now we also need to think about the location. So now we need to know this term in NMR spectrum, which is upfield and downfield. So upfield means your peak is going to be closer to the right-hand side of your spectrum, which has a lower chemical shift or lower ppm. And downfield here means that you have your peaks is going to be more toward the left-hand side of the spectrum, or it will have a bigger chemical shift or ppm. We understand the upfield and downfield in terms of their shielding. So an upfield proton is more shielded, and a downfield proton is deshielded. So what do we mean by shielded and deshielded? So a shielded group of protons means that they have a pretty big electron cloud surrounding the proton, and so it doesn't feel the external magnetic field of the NMR instrument. While a deshielded proton means that the proton, the electron cloud surrounding the proton, is getting pulled by, for example, an electron withdrawing group. And so it feels the external magnetic field more. Okay. So now if we take a look at the keto form, for example, we know that carbonyl here is an electron withdrawing group. So it will pull protons, it will pull electron cloud from these protons with different strength. So for example, if I compare the gamma methyl and the alpha CH2, we can immediately see that the gamma methyl, each of them are connected to only one carbonyl, while the alpha CH2 is connected to 2 carbonyl at the same time. So if I would make a bet, this alpha CH2 will be more downfield compared to the gamma methyl, because it's connected to 2 electron withdrawing group at the same time. So now here, when we check the enol form by itself, we can also see, okay, well, the same principle applies here, I guess, right? The gamma methyl here is only connected to one of these carbonyls, which is now in its enol form, while the alpha CH is connected to 2 at the same time. So this has to be more downfield compared to the gamma methyl. But what about the OH here? So remember, the carbonyl group is electron withdrawing because you have an oxygen here. So oxygen is very electronegative, and the oxygen atom is what is doing the pulling of electron. So here, none of this proton is directly connected to oxygen, while this proton is directly connected to the oxygen in the enol form, which means that this proton is actually going to be in the most downfield compared to this group, and even compared to these groups, right? So now in the enol form, we can see that the ordering is going to be gamma methyl going to alpha, CH going to OH, and it's going to be more downfield in this direction. Okay, so now having said that, we can also analyze what's going to happen between this gamma methyl in the keto form and the gamma methyl in the enol form, for example. Here we have a true carbonyl, while here the carbonyl is not a full carbonyl, because one of them is actually an OH, right? It's just in resonance form. So this carbonyl is actually going to pull stronger than this. So if we check the gamma metal of the ketone and the enol, this is going to be slightly more downfield compared to this one. Here we can also compare the alpha protons. Here, the CH2 is an sp3 carbon, while here the H is connected to an sp2 carbon because there is a double bond here, right? So it's an sp2 carbon. Now, a proton that is connected to an sp2 carbon should be more downfilled compared to one that is connected to an sp3 carbon. Okay. And we will analyze that in more detail once we go to the spectrum. But now we can already see that there is a pattern between the proton in its form, but there is also a pattern between groups of different forms, and we will use that in order to be able to fully interpret the NMR spectrum. Okay. All right. So now once we know their relative positions in the NMR spectrum, we should also check the proton ratio, because the number of the proton in each group correlates to the intensity or the area under each peak in the NMR spectrum. And also their multiplicity. So how will the peak splits? Okay, so let's start with the simpler one, with the proton ratio. So we simply need to count the number of protons in each group. So here we have 6 proton in the methyl group and 2 proton in the alpha proton group. So the ratio of the peak area will be 6 to 2, or we can simplify it as 3 to 1. Here we have 6 in the methyl, 1 in the CH, and 1 in the OH. So the ratio is going to be 6, 1, 1. Next, the multiplicity. The multiplicity of an NMR peak is related to the number of protons in a neighboring carbon. So for example, here, my CH3 do not have any proton in the neighboring carbon here, right? And there's nothing else connected to this, which means that it's going to be a singlet. It's not going to split. And if we check the CH2, the CH, and the OH, it's the same for all of these groups. So that means that all of the peaks that we will see for this compound is going to be a singlet. There's not going to be any splitting. So the situation will change, of course, if let's say I put a methyl group here, right? Or here. Then my hydrogen here and the methyl will be neighbors, and of course they will split. And the splitting is determined by the number of proton on the neighboring atoms. And for more details, I would refer you to the course website. There is a resource about interpreting NMR spectrum, and you can read how a peak will split. Okay. All right. So now let's go to the actual NMR spectrum of this compound and see if we can analyze them based on the knowledge that we already have. Okay. So here I have the NMR spectrum of acetylacetone, which I produced using ChemDraw. So this is not a real measurement. It's just something that the software generated. Here, these numbers are the chemical shift, which is the ppm, the x-axis here, right? So you can see that now we have 1, 2, 3, 4, 5 peaks, as I said, or as we expected, and they all have different chemical shift. So this is upfield, this is downfield, and we will take advantage of that knowledge to assign these peaks. These numbers here in parentheses, they are the peak area of each of this peak. Okay. So now let's start assigning them. So now, of course, the easiest peak always to assign is going to be the OH proton. We know it's going to be the most downfield, which means it's going to be this one, 16.77 with an area of 0.84. Okay, so now we have this knowledge, and then we can use what we know about the proton ratio, about the shift, to our advantage when we are trying to assign all the peaks. Okay, so first we notice that everything here is a singlet, so it's not going to help us to because We cannot use the information about the splitting to interpret the structures, right? But what we can do is we can use the ratio here. So for example, here if I know my OH proton has a peak area of about 0.84, I know that I should have a ratio of 1, 1, 6. And I should see a couple peaks here that would have a ratio of 1 and 6 compared to this OH proton. Well, let's start with the 1 first. So we should be able to analyze the CH, right? Which could be either this peak at 6.19 ppm or this one at 3.61 ppm. So if we check this one, the area is about 1. Of course, it's pretty close, right? But not very accurate. Or it could be this one, 0.5, also a little bit close to 0.84, but we're not sure. The reason why I'm not using this one at 2.25 is because the ratio is this one, it's 2 to 1, right? So it's not gonna match. There's nothing here that has a ratio of 2 to 1 compared to my OH proton. So we're not sure about the CH. Of course, we can already think, okay, my CH of the enol should be more downfield compared to the CH2. So maybe this is my CH. Maybe one of this is going to be my CH2. But we're not sure. Okay. But let's look at this peak that's the most upfield. It has an area of 5.97, right? Which is, 6 times more compared to that. So why don't we assign that, right? And based on what we know, this is also should be in the most upfield group, right? So this means that the 6 is going to be in the gamma metal of the enol. Okay, and again, right? If we compare this group of proton compared to the other ones, we know that this should be in the most upfield group because of the reasons that we have discussed earlier. Okay, so now if we have the 6 and the 1, so I guess we can safely assume that this peak at 6.19 ppm with the area of 1 should be our CH peak, right? And now we see that the pattern match, right? So we go from the most upfield to the most downfield in the enol form, as we have discussed earlier. And the peak area ratio is 6, 1, and about 1. So that sounds about right. So now when we are left with these 2 peaks, right? And we notice immediately that this is more downfield than this. So we immediately can guess that this should belong to our CH2. This should belong to the gamma CH3 of the keto form. And the peak ratio is about 1 to 3, which is exactly what we want, right? So let's just immediately assign them. Okay, so now we have assigned all the peaks to the groups in our compounds. And when we also compare the different groups between the keto and enol, it's also consistent. So as I said, this gamma methyl is connected to carbonyl, so while this one is connected to a carbonyl that is in resonance form. So this should be more downfield compared to this, right? And that's exactly what we see. The keto form is slightly more downfield compared to the enol form. And again, I also said that this proton over here, because it's in it's connected to an sp2 carbon, it should be more downfield compared to the proton here. And that's exactly what we see. This one is 6.19 ppm, this one is 3.61 ppm. So everything matched to what we know, the peak area ratio matched to what we know, so everything looks good. Now, another thing that I should mention here is that when you look at this 2 form of acetylacetone, you might be tempted to think, well, I have 6 protons here and 6 protons here, so their area ratio should be 6 to 6 or 1 to 1. but we immediately see that it's not, right? One is 1.6, one is 5.97, so it's not the same. And you might wonder, but why, right? The reason is exactly what we are investigating actually in this experiment. So this compound exists in an equilibrium between its two tautomeric forms. Now, if the equilibrium constant is not exactly 1, that means you will have more of one form compared to the other. So it could be you have more enol or you have more keto, depending on the value of your K or the equilibrium constant. In this case, we can immediately see that, oh, we actually have more enol compared to the keto, because if we just compare the methyl, and we can see that the peak for the enol form is bigger compared to the keto form. And this information is actually what will give us the value of the equilibrium constant. Okay. So a very important point here is that you cannot use the ratio of the proton groups between different forms. You can only use the ratio in the enol form by itself or in the keto form by itself. So you cannot compare this 6 of this proton, for example, in the keto form to this 1 in the enol form, because the number of your keto and enol molecules are not the same. Okay. All right, so now we have this information, so let's proceed to calculate our equilibrium constant. So to calculate the equilibrium constants, there are many ways to do that here, because you can compare so many different combinations. But for the purpose of making a straightforward comparison, we will only compare groups that are equivalent between the keto and the enol. So what I mean by that is that we need to check the structure of the keto and the enol form, and then we need to see how does each of the proton transform between the keto and the enol. For example, we see here immediately that the methyl groups, the gamma metals, they are equivalent because they stay in the same place and they're not really involved in tautomerism. Right? So that's one possible way of calculating the K. We compare the area of this gamma metal and this gamma metal. Then we can also see that this CH2 transform. So one of the proton goes into the CH. So we can compare this CH and this CH2. And one of them goes to the OH. So we can also compare this OH with the CH2. Right? So now we have 3 possibilities and we will look at them one by one. So the easiest one would be to check at the gamma metal, because we have 6 proton here on the metals in the keto form, and 6 metal here, 6 protons here in the methyl group in the enol form. So the stoichiometry is straightforward because they have the same number of protons. So the first K, therefore, is this the gamma metal of the enol form. We take the area, which is 5.97, divided by the area of the gamma metal protons of the keto form, which is 1.6. So if we take a look at that, just do the calculation, we have the K being 3.73. Okay, looks straightforward. So now let's up the game a little bit. So if we check now the CH2 becoming the CH, now we see that here in the keto form, you have 2 protons per molecule. Well, in the enol form, you have only 1 proton per molecule, right? So that means you have to take care of the stoichiometry. You cannot simply take the area and do the calculation. So what you need to do here is you need to divide the area of the alpha CH2 protons by 2, because 2 protons give 1 molecule. So you need to divide it by 2. So my second equilibrium constant can be calculated as the CH area divided by the half of the CH2 area, as shown here. And if you plug the number and do the calculations, you will get 3.77. Now, last one is the OH of the enol and the CH2 of the ketone. And again, you have a difference in the number of protons, right? Here we have 2, here we have 1. So again, we need to take care of that when we calculate the equilibrium constant. So here we will have the area of the OH of the enol divided by half of the area of the CH2 of the ketone form. And that gives us 3.17. So now you have 3 different equilibrium constant values. So now you can do your analysis. You can take the average, or you can check whether you have an outlier, like this one, for example, and justify why, and do your analysis. Okay, so in summary, first thing you have to do is you have to be able to draw the keto and enol forms of the compound that you have, and you have to do it properly. Sometimes the substituent can be in the alpha position, sometimes it's in the gamma, so you have to know where the location of the substituent is, if there is any. Second, you need to identify the different proton groups in each form. And you have to understand whether the protons will be upfilled or downfilled, based on whether they are close to an electron withdrawing group or not. And then you have to calculate the proton ratio, which will correspond to the area under the peak in the NMR spectrum. And then you have to also check whether the peaks will split based on their multiplicity, based on whether there is a neighboring carbon that has protons. Now, once you have all this information, you can assign the peaks on your NMR spectrum. And lastly, using the area of the equivalent protons, you can calculate the equilibrium constant for the compound. So with this, have fun and play with your NMR spectrum.